In this lecture today we'll be deriving the describing function of dead zone nonlinearity. So looking at the dead zone nonlinearity, we basically have a period on either side of the y-axis where your output is 0. Fine. So this is your output of the system, and we are taking this width that's between the plus and minus side of the dead zone band. Actually we are taking equal to capital D. Fine. So you are applying an input, a sinusoidal input, as we do in case of a describing function. We apply a sinusoidal input. So mapping this non-linearity onto the input, what we see is that for a very brief period of time we'll be getting an output that will be linearly increasing sine wave, and for rest of the period, so between this, so if this is, say for example, alpha, and this is pi minus alpha, so from alpha to pi minus alpha we'll get an output, and similarly on this side we have pi plus alpha and pi plus alpha and 2 pi minus alpha, where we'll be getting the output. And this is your pi. So this is our output with respect to omega t. So therefore, and also assuming that the slope of this dead zone is equal to k. So what we see is our output basically will therefore be equal to 0 for which period, from 0 to omega t to alpha, and it will again be 0 from pi minus alpha to omega t to pi. Fine. And in between our sinusoidal waveform will be equal to kx minus d by 2, where x is equal to x sine of omega t. Alpha omega t to pi minus alpha. So looking at this function that's our output, this is both an odd as well as it has a half wave symmetry. Therefore, when we use the Fourier analysis, we'll be deriving equation for B1 only, while A0 and A1 will be equal to 0. B1 will be equal to 4 by pi 0 to pi by 2 y1 omega t sine of omega t d omega t. Fine. So which is equal to 4 by pi 0 to alpha 0 to alpha, this value will be equal to 0 plus 4 by pi alpha to pi by 2. Fine. We are actually we know that this function has an odd wave symmetry, so we are only integrating from 0 to pi by 2, and we are taking the time period equal to pi by 2. Fine. b1 is equal to 2 by pi 2 by t, that is here since t is pi by 2, so this becomes 4 by pi alpha to pi by 2, and y1 will be for this period k x minus d by 2 sine of omega t d omega t. So that's equal to 4 by pi alpha to pi by 2 k. Now we write k x sine omega t minus d by 2, where small x equal to capital X sine omega t sine omega t d omega t. Fine. So you can integrate this and apply the limits, and also note that x sine of alpha will be equal to d by 2. So using this and integrating this, which will actually imply alpha is equal to sine inverse of d by 2x. So b1 will be equal to 2xk divided by pi by 2 minus sine inverse of d by 2 divided by x minus d by 2 d by 2x minus d by 2x 1 minus d by 2x square. So this will be our b1, and therefore our describing function n of x will be equal to 1 minus, rather it will be k into 1 minus 2 by pi sine inverse of d by 2x minus d by 2x 1 minus d by 2x square at an angle of 0 degrees. Fine. So if we take k at this side, we can find out nx divided by k equal to this, and therefore then we can actually plot n x divided by k with respect to d by 2x. So once you plot this, you'll find this will be equal to a straight line with an initial value of 1 on the y-axis and the final value of 1 on the x-axis. Fine. So if d by 2x is greater than or equal to 1, nx by k will be equal to 0. Fine. So you can actually see it from you can actually apply d by 2x here, and you can see that the nx by k will be defined for d by 2 d by 2x greater than or equal to 1, or in other words we can say d by 2 greater than or equal to x. Fine. So your amplitude of the input, if it is lesser than the dead zone, that actually means so if your uh, amplitude x is actually less than d by 2, that means actually amplitude of input is actually less than the dead zone. Obviously, if this amplitude will never cross into this dead zone, our output will be equal to 0 or at all cases. Say for example, we are talking about a case where sine wave is something like this. Fine, your input is something like this. So if x is less than d by 2, then output definitely will be 0. We'll never be receiving an output in such a case. So this is your equation of describing function for a dead zone. Next, we'll be doing describing function of saturation nonlinearity. And we know that saturation nonlinearity implies that our output basically after some time does not increase and remains constant. This can be at either cases of the of this plane, both the right half as well as the left half of this plane. And again, let us assume the slope of this function is k. We are applying a sinusoidal input. Fine. Let this be equal to alpha, this be equal to pi minus alpha. So what we'll be getting at the output? So as long as our output is varying from 0 to alpha, we'll have a sinusoidal response. Then our output will be flat for this period from alpha to pi minus alpha. This will happen at either end of this axis. So this is pi plus alpha, this is 2 pi minus alpha. So what we are saying in this case, if we apply a sinusoidal input to a saturation, we'll get an output response like this, y of omega t. Fine. And if this is equal to k, say for example this is equal to ks rather, and this is our x, small x equal to x sine omega t. So accordingly we'll be getting our output response will be limited by the saturation block whose amplitude max is k of s. So y of omega t will be equal to, it will be equal to k x sine omega t for 0 to omega t to alpha. Fine. It will be equal to k of s for alpha to omega t to pi minus alpha, and it will be equal to again kx sine omega t for pi minus alpha to omega t to pi. So this will be our output For this case, again, this is an odd function. Sinusoidal function is always an odd function. Uh, now there will be actually two cases in this case. Uh, there will be actually two cases. Case number one will be where our s divided by x is actually less than 1. If our this, the value of this s divided by this x, the amplitude of this sinusoidal function, is less than 1, that means actually s by x is actually less than 1, means actually x is greater and it actually goes into the saturation region, right? So if this is less than 1, that means our output is actually basically saturated. Then our output, as shown, our output will be as like this, right? In that case, you'll again find out b1. When you find it out, you see it will be equal to 2kx divided by pi sine inverse of s divided by x plus s by x 1 minus s by x whole square, right? So this will be our b1. Similarly, you can find out phi, it will be equal to 0 again. So therefore, n will be equal to 2k by pi sine inverse of s by x plus s by x 1 minus s by x square angle 0 degrees. So this will be our describing function for the first case, where s by x will be less than 1. In that case, actually our output will be equal to this, fine. In the second case, where s by x is greater than 1, that means x actually uh, the magnitude s is actually greater than x. That means that actually implies s is greater than x. That means our output will simply be a sinusoidal waveform, because it will never go into the saturation region. There will be no saturation effect in this case. So what will happen is that the describing function, when we find it out, y by x will be equal to 1 for this case. So if you see the relationship between the, if you see the two cases, in the first case there is saturation and our output will be governed by those describing function as shown. In the second case, there is no saturation. Describing function will simply be equal to 1, because our, why is it be equal to 1? Because our input and output basically will be the same sinusoidal function. There is no saturation effect, so y by x will be simply equal to 1. They will simply cancel out each other. Now if you see the relationship that we have done dead zone and saturation today, relationship between dead zone and saturation of the describing functions that we have actually obtained, you will see that from the two cases, if s is equal to d by 2, where s was actually the amplitude of the saturation, if this is equal to d by 2, where d by 2 was the uh, width of the dead zone nonlinearity, and if you put this equal to that, you see the describing function of dead zone will be equal to k minus the describing function of the saturation block. Right? So you can actually see this relationship from the describing functions that we have derived today. One of dead zone and another one of saturation. So you can actually use the Fourier analysis to calculate V1, the saturation on. For the case of saturation, you can find out what will be the value of V1. Fine. Again, since this is an odd function, half-wave symmetry, A0 as well as A1 for the saturation case as well as for the dead zone case will be equal to 0. Let's do another case. Let's do the describing function of dead zone with saturation. So we are now actually using two different non-linearities together. That means for a brief period of time our output response is 0, then it increases and then it becomes constant. It goes into the saturation. So similarly on the negative half side you will see a relationship like this. So you are having a function, nonlinear function like this. You are applying an input to this. Fine. So in this case now there will be three cases that you will study, and accordingly you can find out the output waveforms for the three cases. For case 1, where amplitude of sine wave will be less than this, our output will be equal to 0 actually. Fine. Where I will put this is equal to D and this is equal to S and this is equal to X. Fine. So if X is less than D, then our output will be simply equal to 0. In second case, if our X is somewhere, it is between D and S, that means somewhere in this portion. This is D is on the x-axis, S is on the y-axis, so this is not exactly a proper way of describing this, but you can understand this what I am saying. Our input is lying somewhere in this region. So in that case, what will happen is for some period of time, say for example for alpha times, that's from 0 to alpha, there will be dead zone, then you will have a sinusoidal function, and this will be pi minus alpha, and similarly on this side, pi plus alpha, 2 pi minus alpha. So this will be case number 2. And case number 3 is where x will be actually greater than s. That means our sinusoidal function will be somewhere here. So what will happen in this case? Our output, again after alpha there will be an output, then it will go into saturation, then it will fall. Alpha, pi minus alpha, then similarly pi plus alpha, saturation, 2 pi plus alpha. Fine. So there are actually three cases that you need to understand for this particular function, where x will be between 0 and d, then output will be actually 0. Fine. Where x will be between somewhere lying between d and s, rather d by 2, mark this d by 2 and s. So where s is basically greater than d by 2 but less than s. Fine. X is greater than d by 2 but less than s. So you will get this type of function that you need to solve, and in the third case you will get this type of function that you need to solve. So this type of case that we have already found for the dead zone. This is similarly a simple dead zone that for which case we have already found out the equation. We need to find out the equation for this case now, this third case. So again, it has a half-wave symmetry. it's an odd function, so b1 you have to find out b1. So b1 0 to alpha it will be 0, alpha to say for example this is beta here, so alpha to beta it will be equal to x sine omega t, fine. And from beta to, so if you are going for half wave symmetry, beta to pi by 2 it will be equal to constant, that is k s, fine. So you'll find out the values of you'll find out b1 for this case, and so this is actually a job. This is an assignment for you. You find out the describing function of dead zone with saturation for the third case. For this case, describing function will simply be 0. For second case, we have already found out the describing function of dead zone. This will be similar to that. For the third case, you have to find out the describing function. Y of omega t will be equal to 0 for 0 to omega t to alpha. It will be equal to kx sine omega t for alpha to omega t to beta, and it will be equal to ks constant then beta to omega t to pi by 2, fine. So you can find out for time period of pi by 2, and you have to find out the value of b1, fine. You can find out the describing function for the system. So this is one case. Similarly, next we'll do in the next session. So this is for today. Find out this describing function of dead zone, saturation, and dead zone with saturation.